Okay. Hi everyone, I'm Shengyuan. Today I'm going to share our work, quantum assertion testing without mid-circuit measurement, strategies and law bounds. It's a work done by me and Charles Yuan, and we are from University of Wisconsin-Madison. So our topic here is quantum assertion testing. But first of all, why do we even want to test quantum programs? Well, it is because quantum programs are really hard to reason about. Here's an example on the Grover's paper. On the left, you can see the algorithm as it was described in the original Grover's paper. And on the right, there's a version written in one of today's most high-level quantum programming languages. While this is a little bit complicated, the fact is, in this algorithm, we see things like loops, function calls, and array accesses. And those are exactly the kind of places where bugs can show up when people try to code them. So I'd argue that it would be really useful if we could test these programs by inserting runtime assertions to check the program state, just like what we do when debug classical programs. As we know, in quantum computation, we are manipulating qubits, which is usually in a superposition of kit 0 and kit 1. It only collapses to a classical 0 or 1 when we perform a measurement on it. So this means we can't really learn anything about a quantum state unless we actually perform a measurement. Now, if we think of executing a quantum program as applying a sequence of quantum gates on qubits, and imagine we've inserted some assertion circuits, these little black boxes, into the circuit. Then to check whether the program state satisfies some certain predicate during runtime execution, the most straightforward idea is to just measure those qubits. But we generally don't want to do that, because measuring the program qubits would collapse their states, which usually disturb the rest of the computation, and that's a problem if we want the program to keep running correctly. So to actually learn from assertions in a quantum program, pioneer works have proposed to use ancilla qubits to get toggled when an assertion fails. Then, instead of measuring the program qubits directly, we just measure those ancilla qubits. For example, here we have two ancilla qubits, each get toggled by the outcome of one assertion at runtime. Then we can defer the measurement of these two ancillas till the end of the program. Another thing we might want to do is to reuse the same ancilla for multiple assertions. The idea is you measure the ancilla in the middle of the circuit to check one assertion, then reset it to cat 0 and reuse it for the next one. That sounds nice. It saves ancilla qubits by recycling the same one each time. But here's a catch. This approach relies on mid-circuit measurement, which means performing a measurement in the middle of the quantum circuit. And such physical operation is inefficient and can be hard to support in current quantum hardware, so we might want to avoid that if possible. And this brings us to the core question of our research. For a quantum program with n assertions, we want to understand, without the use of mid-circuit measurement, how many times we need to run the program and how many ancilla qubits we need in order to detect whether any assertion fails, and also to identify the first failing assertion. We call these two problems the exist-fail problem and the first-fail problem. In classical computing, it is trivial. No matter how many assertions in a program, a single run with one bit of outcome is enough. While in quantum setting, things are much less obvious. One of our key results is that if we consider a single run setting, then for both these tasks, first-fail and exist-fail, the required space overhead has a tight seed-login bound. Now, to better illustrate our motivation, let's look at a few very simple quantum program snippets to get a feeling of what kind of assertions we might want to test during runtime. For the first example here, x is an arbitrary qubit, and we initialize y to kit 0. We apply a CNOT gate controlled by x and targeting y. After this operation, the result is alpha kit 00 plus beta 11, and this is a typical entangled state. So at the end of this code snippet, we might want to check whether in each branch x equals y at runtime. And if we have a way to perform assertion checking like this, say assert x equals y, then it should give us a pass if the code does not contain any bug. In the second example, we start by preparing z in the cat 0 state, and then we apply two consecutive hard mod gate on it. And the final state will still be in cat 0, so we might want to write an assertion like assert z equals 0 to debug the code. For the third example, The only difference from the previous one is that we add a phase flip, a Z gate, right in the middle of the two hard-mode gate, and it's controlled by a classical input bit. With that, the final state of the qubit y ends up matching the classical input bit. So if we assert y equals 1 here, then it will pass if the classical bit is 1 and the program is correct. Now what we really care about is that if we combine those three code snippets together into a single program and put the three assertions we want to check exactly where we want to check them at runtime. Now we have three runtime assertions in a single quantum program. As we mentioned earlier, in such situation, we don't want to directly measure the program qubits x, y, or z at those assertion points, because that would collapse the state and disturb the rest of the computation. So how do we actually check these assertions? Well, the trick is to route each assertion's runtime outcome into an ancilla qubit, so that we don't have to measure the program qubits directly. Instead, we can just measure the ancilla qubits to learn the outcomes. Here, for each of the three assertions, we use an oracle unitary to write the assertion's runtime outcome into an ancilla qubit. The exact design of these oracle operations, these O1, O2, and O3 shown on the slides here, depends on the type of those assertions we want to check. For example, the oracle for the first assertion A1 consists of performing two CNOT gate targeting an ancilla A, and the oracle for assertion A2 and A3 can be instantiated by a single CNOT gate targeting their corresponding ancilla qubits B and C respectively. Well, existing literatures on quantum assertion have studied this in detail. They have studied the expressiveness of assertions and how to realize the checking for them at runtime, which gives what these oracle unitaries actually look like. But in this work, we just treat them as oracles, and we don't care about their exact circuit structure, and simply assume such oracles exist and can be invoked. Then we can simply defer all measurements of these ancillas to the very end and learn all three assertion outcomes within one run. If we generalize this approach to a quantum program with n assertions, we will use n ancilla qubits, each get toggled by one assertion outcome. This is what we call the single-run n ancilla strategy. In this strategy, we only run the program once, but with n ancillas. Do we have other options? Well, instead of running the program once with n ancillas, we can run it multiple times, each time enabling only one assertion, and just use one ancilla to store that outcome. So in the first run, we enable only A1 using a single ancilla to capture its outcome, and then measuring it at the end of this run. And in the second run, we enable A2, reuse the same ancilla A, and measure it again at the end to learn the result. And in the third run, we do the same thing for A3. So overall, we reuse one ancilla across multiple runs and learn one assertion outcome per execution. And this is what we call single ancilla n-run strategy for a program with n assertions. And now let's take a close look at these two baseline strategies we described and consider the resource used. Both strategies satisfy the trade-off of form t times s equals On, where t is the number of executions, and s is the number of ancilla qubits used per execution. And the natural question to ask is, can we have a strategy that achieves a better of all trade-off? Well, one thing we may want to do is that if we allow mid-circuit measurement, and we can reset measured qubits for later use, in that case, we can reuse the same ancilla for every assertion within a single run. This idea is, after each oracle invocation, we just measure that ancilla immediately to learn the assertion outcome, and then reset it back to fresh, so it's ready for the next one. For example, here we only use the same ancilla A 3 times, and measure it 3 times during a single run. And this approach uses only one ancilla and performs just one run for all n assertions. This seems to be a better solution. However, such strategy relies on mid-circuit measurement, and a previous study have shown that this physical process, measuring qubits at the middle of the circuit, is kind of slow and relatively hard to support in current quantum hardware due to latency and noise sensitivity. and that is why we may want to avoid doing that if possible. And our work is to discuss if we could design a better strategy to learn from runtime assertions without the use of mid-circuit measurement. In our problem setting, we consider a program with n-indexed assertions, A1 through AN, each inserted at a different point of the program. In terms of the semantics of each assertion, we abstract them as assertion checking oracles. The definition of this oracle is shown on the slide. It applies on the program state psi and an ancilla qubit AI. The oracle keeps the ancilla unchanged for the assertion passing branch, but toggles the ancilla failing branch by XOR the value of the ancilla by 1. From this definition, we can see that, depending on the bucket program and the assertion, the outcome of the runtime assertion may not be a deterministic 0 or 1, it may instead be in a superposition of pass and fail. While in this talk, for ease of presentation, we restrict attention to the case where the assertion outcome is deterministic. For the more general case, where the outcome can be in a superposition of pass and fail, we can declare an assertion to fail when the state has some failing amplitude, then detect via efficient sampling. We will include the detail of such kind of discussion in the next version of our paper. We then define our single-run and multi-run strategy. A single-run strategy is basically an instrumented execution of the program. This instrumentation has to specify two things. First, which assertions are enabled in this run, and how the assertion checking is carried out. More concretely, it includes how we initialize the ancilla pool, and then for each enabled assertion AI, we invoke the oracle unitary OI to write the assertion outcome into some chosen ancilla qubit. And after that oracle call, the instrumentation can also apply an arbitrary unitary UI on the ancillas to do whatever additional computation it wants. At the end of this run, we measure the ancillas used in this execution and obtain some classical bits. For a multi-run strategy, we simply allow multiple such instrumented executions, and we further classify multi-run strategies along 2 dimensions: whether the enabled assertion sets are disjoint across runs, and whether adaptivity is allowed. Now let's talk about some of our results. First, consider the exist problem in the single run setting. In one execution, we want to detect whether any of the n assertion fails. For this problem, the space law bound we established says that we need at least omega log n ancilla qubits. Well, this is a little bit surprising because information theoretically, the answer is only 1 bit, failing exist or not. The reason we still need log n space here is that the computation on the ancillas has to stay reversible. For the proof of this law bound, we look at a canonical program where the program qubits holds a length n 0-1 bit string w, and the program itself applies just identity throughout the execution. For the n assertions, we define that the ith assertion to simply check whether the ith bit of w is 0. And the overall effect of assertion checking gadget OI plus UI on the ancilla register for this program can be seen as performing one of the 2 permutations, PI0 or PI1, on the ancilla species state, depending on the ith program bit being 0 or 1. At this point, the exist fail problem reduces to a problem on a finite state permutation automata. The number of automata state is the number of ancilla basis state. The automata reads an input bit string w of length n, which just corresponds to the bit string stored in the quantum program. And when the automata reads the ith bit, it updates its state by applying either PI0 or PI1. So the question, how many ancilla qubits do we need for exist fail, now becomes how many state do we need for this permutation automata to compute the ON problem. For this problem, we prove it needs at least n plus 1 state. The proof has 2 steps. We first prove a pumping style lemma. Then we use a counting argument, which considers inputs with different O0 prefix. We show that the automata must end in pairwise different state after reading such kind of inputs. Putting this together, we get that the automata needs at least n plus 1 distinct state. This means we need at least omega log n ancilla qubits. For the upper bound of the exist field problem, we give a strategy that uses a mod n plus 1 counter with all log n ancillas. So this log n space bound is tight. Next, still in the single run setting, we look at the first fail problem. In one execution, we want to identify the position of the first assertion that fails. We show the ancilla lower bound is also omega log n. This can be proved by either reducing from the exist fail lower bound or more directly from an information theoretic accounting argument. And as I'll mention on the next slide, for FirstFail, we can also construct a strategy that matches this log n bound. So unlike exist fail, here requiring the computation on the ancillas to stay reversible does not impose extra restriction for this problem. Here we provide one possible construction with all log n space for the first fail problem. In a single run, we use two pieces of ancilla, a 1-bit flag qubit f and the index register whose size is log n plus 1 qubit. Then for each assertion we encounter, we do 3 steps. First, we call the assertion checking oracle to write the assertion outcome into the flag f. And next, we do a controlled update on the index register, controlled on f. If f equals 1, we swap the all 0 basis state with a basis state that encodes the current index I. Notice that such kind of operation is reversible. And finally, we uncompute f back to 0, so we can reuse the same flag qubit for the next assertion. In the end, the index register contains exactly the binary encoding of the first failing assertion, I star. Finally, I want to give a brief summary on our results for multi-run settings. If we consider disjoint assertion sets and allow adaptivity across runs, then we show a lower bound for both problems of the form 2 to the s times 2t equals omega n, and we further show this lower bound is tight for both problems. And if we consider general assertion sets but no adaptivity across runs, then we establish a lower bound of a different form, which is s times 2t equals omega log n for both, and we further show for exist fail problem this is tight. For the details of the multi-run setting, please refer to the next version of our paper. So to sum up, we initiated the study of time-space trade-offs for checking multiple assertions in quantum programs without mid-circuit measurements. And we established non-trivial lower bounds and strategies for the exist fail and first fail problem under different settings. In the near term, it would improve our ability to test quantum programs on hardware platforms where mid-circuit measurement is costly or unsupported. And in the long run, the strategies we propose also require fewer measurements compared to mid-circuit measurement strategies. And that's it, the end of my talk, and I can take questions.
Questions?
Thank you for the talk. It was so interesting. But I might say something like very stupid. But does it make sense to assume, for example, like at most one failure might have occurred, can occur, and like improve the strategy or something like that?
So you don't need to assume that at least one failure occurs, because you see we have the problem of deciding if there has any existing failure.
Yeah.
So if there is no existing failure, then the existing fail problem should give us the result that there is no failure.
Okay, thank you.
All right, let's thank our speaker again.